You know, machine learning can sound super complicated, right? But what if I told you we could break it all down like we're building a house? Today, we're digging into some fantastic research material from Dr. Sudheendra S G to give you, especially if you're an educator, a really simple, powerful guide to this world. So let's get started and lay the foundation.
So it really all boils down to a question that every single educator out there knows by heart. How do you teach someone to spot a pattern? Well, machine learning is really just about getting a computer to do that exact same thing, to learn from examples just like one of your students would.
All right, so let's stick with that construction idea. Before you can build anything, you need a blueprint, right? For us, that means we first have to get a clear picture of the relationship between artificial intelligence and machine learning.
So, artificial intelligence, or AI, that's the big dream. That's the finished skyscraper. It's the grand vision of creating systems that can do things we normally think only humans can do, like reasoning or perceiving the world around them. Okay, so if AI is the finished building, how in the world do we actually build it? Well, that's where machine learning, or ML, comes in. You can think of ML as the toolbox. It's not magic, it's a practical set of power tools and techniques that lets a system learn how to do those intelligent things by finding patterns in data, instead of us having to write code for every single tiny step.
So here's the big picture. You've got AI as the goal, and machine learning is one of the most powerful sets of tools inside that field. And in that toolbox, you've got three main types of tools. For our little project today, we're going to focus on the one you'll see most often, which is called supervised learning. And that's all about learning from examples that already have the answers attached.
Okay, so every build needs materials, right? You need lumber, you need concrete. Well, for supervised machine learning, our raw material is data. And more specifically, it's something called labeled data, which is just a fancy way of saying we have a whole bunch of examples where we already know the right answer. So to make this feel a little more real, let's actually get our hands dirty and build something. We're going to build a classifier. Our job is to teach a computer how to tell the difference between two kinds of moths, the emperor and the Luna, just by looking at a couple of their physical measurements.
Now take a look at this. This table is exactly what the machine sees. It doesn't get to see a beautiful photo of a moth. Nope, it just sees rows and columns of numbers. You can think of this as its textbook. Each row is like a flashcard. Here are the measurements, and here is the correct name of the moth.
All right, let's break this down even further because this part's important. The columns we use to make the prediction, the wingspan and the mass, we call those features. They're the clues. And the column we're trying to guess, the species, that's the label. That's the right answer. So the features are the question, and the label is the answer key.
Okay, we've got our blueprint, we've got our materials. I think it's time to pour the foundation and put up the first frame. Let's build our very first simple model.
So what if we took all that data and just plotted it on a simple chart? You know, wingspan on one side, mass on the other. Suddenly, our job gets a lot clearer. All we have to do is draw a line that separates the emperor moths from the Luna moths. And get this, that simple line, that is our model. Now, this line has a fancy name, of course. It's called a decision boundary. But all it really is the rule the computer's going to use. If a new moth lands on one side of the line, it'll call it an emperor. If it lands on the other side, it's a Luna. It's really that straightforward.
And here's how that line on a graph actually turns into a set of instructions for the computer. At its core, a model can just be a simple if-then statement. See, it's not some kind of magic black box. It's just logic, pure and simple logic, that it learned from the data we gave it. But, just like building a house, just because you've put up the walls doesn't mean it's a good house. We've got to do some quality control. We need to check for any major flaws that could make our model totally useless out in the real world.
And that leads us to two classic mistakes you can make. On one side, you've got what's called underfitting. This is where your model is just too simple. It's a sloppy line that totally misses the real pattern. But then there's the other extreme, overfitting. This model is way too complicated. It wiggles and zigs and zags to perfectly nail every single data point we showed it. The problem? It didn't learn the pattern, it just memorized the answers.
And this brings us to what's maybe the most important concept in all of machine learning, generalization. See, we don't care if our model can ace the practice test. What we really want is for it to ace the final exam, to make good predictions on mobs it's never ever seen before. That's what true learning looks like.
So, how can we be sure our model has actually learned? Well, the solution is brilliant, and it's absolutely fundamental. We just split our data. We show the model one chunk to learn from, that's the training set. Then we tested on a separate chunk we kept hidden, the test set. It's the only way to know if it's learned or just cheated by memorizing.
You know, that simple line we drew? That was kind of like building a shed with a handsaw and a hammer. It works, for sure. But in our toolbox, we've got some serious power tools. So let's take a quick look at a few of the more advanced algorithms out there.
First up, we've got decision trees. Now, you can think of these as a much smarter version of that single if-then rule we made. It's like a whole flowchart of questions. And it gets even cooler when you combine a bunch of them into what's called a random forest. Basically, you get a whole committee of these trees to vote on the right answer. Pretty clever, right?
Next up is something called a support vector machine, or SVM. And this one has a really cool trick up its sleeve. It doesn't just find a line to separate the moths. It looks for the one best line that creates the biggest possible buffer zone or margin between the two groups. It's all about finding the safest, most confident dividing line it can.
And finally, the big one, neural networks. Now, these are loosely inspired by how the human brain works. They use all these layers of connected little units to find incredibly complex patterns, stuff that a simple line could never dream of. When you hear people talk about deep learning, all they mean is a neural network that has a ton of layers. And these are the engines behind things like image recognition and those crazy smart chatbots we're all seeing now.
So we've built our model. It's looking good. But wait, before we can cut the ribbon and open it up for business, there's one last, absolutely critical step. We have to make sure it follows the building code. And in machine learning, that means thinking really hard about ethics and responsibility.
Because we have to be really careful. If you train a model on data that has old biases in it, guess what? The model will learn and even amplify those biases. It can accidentally leak private, sensitive information, and, just like any powerful tool, it can be used for things it was never intended for, some of them harmful. That's why things like fairness and privacy can't be an afterthought. They have to be part of the blueprint from the very beginning. And that really brings our whole building project full circle. Dr. Sudheendra sums it up perfectly here. AI is the ambition, ML is the toolbox, data is the fuel, and evaluation and ethics, they're what keep us on the road. So we've kind of demystified the how of it all. But maybe the bigger question, especially for all you educators out there, is now that we know how these incredible tools are built, how are we going to teach the next generation to build them responsibly?